Hello, this is the video abstract for our 2025 climate paper, volume 13, paper 226. Let us change the aerodynamic roughness length as a function of snow depth, with lead author Jessica Sanow, myself, Stephen Fassnacht. So let's consider the wind profile across a surface. Here we're thinking about the snowpack surface. In stable conditions, it is a logarithmic profile. We know that air is compressible, so it's not necessarily stable. But we have this key component, this key often used as a parameter, Z naught or Z naught, that is not necessarily constant. This is crucial in calculating the sensible and latent heat fluxes, as well as movement of snow through redistribution. So let's consider Z naught and snow. We often assume that the snow is flat and Z naught is constant once the ground is covered. But here we have a series of different examples from snow on a lattice, sastrugi, sun cups, some melt rills, and different characteristics of roughness due to light absorbing particulates that illustrate that the snow surface is not flat and not constant. So that Z naught value is variable. We hypothesize that as the snow starts to accumulate, that Z naught value changes. So we have an initial value of the ground Z naught, and then once the snow starts to accumulate, depth goes up and our Z naught value decreases. Then midwinter, once the snowpack is disconnected from the surface, we have a constant Z naught value and the snow depth can continue to increase. And then potentially hysteresis in the correlation between Z naught and snow depth as the snow melts out. And we may have a different, slightly lower Z naught value of the ground surface due to compaction of the vegetation. We collected data over the winter of 2019-2020 in northwestern Colorado in the White River watershed at 9 different locations. Some of these we had measurements weekly, bi-weekly, Julie Circle. We went out whenever the snow fell. And we had 91 data points that we used to assess the nature of Z naught versus depth and that hypothesis that we just illustrated. We then took this dynamic or variable Z naught correlation that we found and modeled sublimation. We can see that we got from our Julie Circle site near Meeker, Colorado, and we saw that we had about 24 millimeters of sublimation using the bulk transfer formula, whereas if we used a constant Z naught value such as 0.24 millimeters as used by the community land model, we only got about 13. Check out our paper.